Hi, everyone. Welcome to the online version of today's seminar. Today, our speaker is Tracy Ka. She's an associate professor of statistics at Harvard University. She recently received a Sloan Research Fellowship, the IMS Peter Gavin Hall Early Career Prize, the ASA's Gottfried E. Nether Young Scholar Award, and an NSF Career Award. So quite a lot going on. Her research interests include high-dimensional statistics, machine learning, social network analysis, text mining, bioinformatics, and statistical genetics. So I'm very excited to see what she has for us today. And Tracy, you can take it from here.
Okay, thank you. Let me share my screen now. Oh, sorry. I think. Good morning, everyone. I want to thank Trevor for the very nice introduction. I also would like to thank Ray for inviting me to visit and give a talk. I visited this department a few years ago, and it was really great to come back. Although due to the emergency of building closed, I cannot meet everyone in person, but I look forward to our meetings on Zoom. Today, I'm going to report some of my recent works on text data analysis. I will start from advertising a dataset collected and cleaned by our own. At first glance, this kind of data seems to be very everywhere available in Google Scholar, in Web of Science, for example. However, all those online search engines only allow you to do small queries rather than massive downloading. So we spend a lot of time collecting and cleaning these data sets and make everything in the ready-to-use format. And the data sets can now be downloaded from either the journal websites or my GitHub page. Okay. There are some other data sets available of this kind, but they only contain the summary statistics, like the journal level summary statistics. But for our data set, we have the detailed attributes for every paper. And using this data set, we can study a lot of problems. And one kind of data that you can access in this data set is the unstructured text abstracts. Okay. So I took the liberty to generate the word cloud using the 216 paper abstracts of Professor Raymond Carroll in this data set. Okay. So for every author, we can generate such a word cloud, and we can see that the patterns for different authors will be different. But the question is that, is there a principled way to extract information for such unstructured text data? So today I'm going to ask the following questions. What are the main topics in statistics? And then given these main topics, what is everyone's interests over these topics? And then what are the trends and patterns in statistical research? I believe everyone has your own answer, but I want to get an objective and a data-driven answer by doing topic modeling. So a high-level idea of topic modeling is as follows. I will input the text abstracts and specify the number of topics, say 11. Okay. Then the algorithm will output the following. The first is the K estimated topics. Okay, and each topic is represented by a distribution on the dictionary. It also outputs the weights of each paper on these different topics. So I can use these to study the research interests of individual authors. Okay, if I were giving this talk a year ago, I could now start presenting my model and method. But nowadays, a lot of people will ask, why not using the large language models? Okay. So I did try using the LLMs to answer these questions. Okay. The most common way of using these pre-trained large language models is through fine-tuning. So this LLM is just a very complicated nonlinear deep neural nets that can map any text into some feature vectors. And then we can couple it with another statistical model for prediction task. Okay. And then for this part, we have some, we have some pre-trained parameters. But then in the fine-tuning process, we just retrain all the parameters in this model. Okay. So as you can see, if I want to use the fine-tuning approach, I must have some training labels Y. But unfortunately, the problem I posted here is an unsupervised learning problem. I don't have the already labeled text abstracts of topics. So I cannot do this. Okay. Then my second attempt is using the recent chatbots like the ChatGPT. Okay, so I asked an undergraduate to focus on doing this, and he tried using different prompts. So a prompt is the question we ask to ChatGPT. So if you ask different questions, ChatGPT will give you different answers. And there is a lot of study about the prompt engineering. So in our prompt, we want to make sure that the topics ChatGPT give are for statistical professionals rather than to general public. Okay, and also a very important thing that we want to make sure that the results are reproducible. That is, every time we ask the question, we get the same answers. So we add a line called code approach. And usually ChatGPT will output some code. Very interestingly, if we take a look at the code from ChatGPT, we find that it basically just called a topic modeling algorithm. So eventually, ChatGPT seeks the help from the statistical methods. Okay. So from these attempts, I try to say that although the artificial intelligence and large language models have gained a lot of successes and everyone is discussing about, and as statisticians, we think we should embrace this trend. But it doesn't mean that we should abandon the more classical statistical methods. Before these LLM get popular, the statistical methods are already proved to be very successful. And they are especially suitable for the following cases. Well, as a researcher, we don't have like hundreds of millions of documents as high-tech company. We just have a couple hundreds and thousands documents from our own study. And we don't have GPU as well as an engineer to help us train those DNNs. So we want to have some easy to compute approach. And we face unsupervised learning problems where we don't have carefully manually labeled data. And also we want to have a white box approach where we know how to interpret and diagnosis for the results. And then statistical methods can satisfy these purposes. And today I will talk about topic modeling, which will be a great example for this. Okay, so in the first part of the talk, I will introduce some recent methods we developed for estimation and inference in topic models. Okay, we convert each document into a word count vector. So if we have n documents in total and p dictionary words, and then we get a p by n word count matrix. Okay, this is our data. And then our parameters include the k topic vectors. Okay, so the rationale is that although n and p can be both very large, we think these documents are generated by a relatively small number of topics. For example, k equals to 10, 20. Okay? And each topic is a dictionary over the p words. So therefore, it's represented by a p-dimensional probability mass function. Okay? Additionally, for each document, it admits a k-dimensional weight vector specifying the weights of different topics. Okay, so let's think about the statistical research. For example, we have a topic that is non-parametric, and then this AK will have more masses, like higher frequencies on words, such as in kernel bandwidths. And then we have another topic that is the Bayesian statistics, then that AK will have more large entries on words in like prior and posterior. Okay, and then if I take a document, if this document is 80% in non-parametric and 20% in Bayes, and then the WI will be a two-dimensional vector, 0.8, 0.2. Okay. Given these parameters, then how do we assume the data generating process? We think that each document has its own population frequency vector, omega I. Okay, so if this document is 100% in one topic, then omega I will be equal to one of the topic vectors, the AK. In the more general case, this document can have weights on different topics, and then omega I is a convex combination of the K topic vectors. Okay, so after we have this omega I, then how do we generate words? So we just draw words from the dictionary sampling with replacement. And then the sufficient statistics are the word count vector, and it follows a multinomial distribution. Okay. To summarize, in our model, we have a P by N data matrix. So each column of this data matrix is the word count vector for one document, and we assume that it's a multinomial distribution, and the number of trials is just the length of this document, and the probability events are from the convex combination of topic vectors. Okay, so we are so here Ni serves more as a nuisance parameter. So we are often work on these normalized empirical word frequency vectors matrix D. And under this model, D admits a low rank factorization in this way. And the problem, the goal is that given the data matrix D, and we want to estimate A and W. Okay, so the topic model itself is actually not identifiable. So we need some identifiability condition for that. One popular identifiability condition is the anchor word condition. Okay, so here I put the K topic vectors together. I get a K by P by K matrix. If I look at it column by column, it's topic. But if I look at it row by row, each row represents a word. Okay, so if this word has a non-zero entry in one and only one topic, and then this word is called an anchor word of this topic. It means only when this topic is discussed, we can see this word appearing. So for example, if the topic is Bayes, and then prior can be an anchor word for the Bayes topic, and the lasso can be an anchor word for the high dimensional statistics topic. Okay, and we will assume that each topic there exists at least one anchor word for each topic, so that each topic is identifiable. And we don't need to know which words are anchor words. We just need the existence of anchor words. Okay. And then under these model and identifiability conditions, we seek for efficient algorithms for estimation. So in the literature, more than 90% of the works in topic modeling are from the Bayesian literature. So they put priors on WIs and then use variational inference to get the posteriors. Just the recent years, the frequentist approach started to draw more and more attention. So in this frequentist approach, we just view that the topic model is basically a factorization structure on the word count matrix. So the A and W are two factors, and they are just arbitrarily unknown parameters. Okay, so we want to use the frequentist approach to estimate these two factors. Okay, so given this literature, what's the contribution of my work? So when I started to learn this topic model, one thing that really surprised me is almost no one used the principal component analysis. As a statistician, we know that whenever we see a low rank structure behind, whenever we know there is a low rank structure behind the data matrix, our first reaction is that I want to use PCA. At least it's very fast because it's a huge dimension reduction. But why didn't people use PCA? There were two big challenges. The first challenge is that the principal components are by themselves not valid estimates of the topic vectors. So we need to figure out the unknown connection between the PCs and the target topic vector. Okay. The second question is, the second issue is that the text data have very severe heterogeneity. In natural languages, we often have the Zipf's law, which means the frequencies of some words can be hundreds of thousands times higher than the frequencies of some other words. And the textbook tells us that we should only use PCA if the data doesn't have severe heterogeneity. If the data has severe heterogeneity, the accuracy of PCs will be very poor. Okay. So today, I will try to resolve these two challenges and introduce a spectral algorithm for topic modeling. This spectral algorithm is called a topic score. But before I present the algorithm, I want to show you some incentive of doing the PCA. Okay. So LDA represents for latent Dirichlet allocation. It's the most popular approach from the Bayesian literature. NMF represents the non-negative matrix factorization, the most commonly used one from the frequentist approach. And we can see that if we are able to use PCA for topic modeling, at least we gain a really huge improvement in computing time. It's very, very fast. Okay, so the question is that how can we use PCA to do that? Okay, so I will now introduce my algorithm. My algorithm has two parts. So in the first part, I try to create some low-dimensional embeddings of words. Okay, I will do singular value decomposition of the data matrix. But instead of doing the plain SVD, I will need to combine it with careful normalizations. So here, this M is a diagonal matrix, where the J's entry diagonal of M is just the average frequency of word J. Okay, so you can see here, what I do is that I will normalize each row of the data matrix by the square root of the average frequency. So therefore, the high frequency words get down-weighted and the low frequency words get up-weighted. Later, I will explain why I do this. The main purpose is to improve the signal-to-noise ratio in SVD. Then after I do SVD, I get the leading singular, the K leading left singular vectors. Okay, but the heterogeneity still exists. So to further remove heterogeneity, I will do a post-SVD normalization. And in this normalization, I use Kasai 1 to normalize the remaining singular vectors entry by entry. And this normalization is now well known in the network data analysis called score normalization. I just adapted it to text analysis. Okay, and so after this, I get a P by K minus 1 matrix. Then if I look at it row by row, each row is a low dimensional embedding of a word. Okay, so it turns out that there is a simplex geometry associated with these low dimensional embeddings. So this plot shows the rows of R hat in the noiseless case. K equals to 3, so each row is in dimension 2. Now you can see that the rows form a triangle, and the anchor words for each topic are located exactly on one vertex of this simplex. Okay, so therefore, provided that there is at least one anchor word per topic, I can just immediately get this simplex by computing the convex hull of the data points. Then after I get the vertices, now I can rewrite each point uniquely as a convex combination of the k vertices. This combination coefficient is called pi I. It's called the barycentric coordinate of this point in this simplex. If I stack these barycentric coordinates together, I get a P by K matrix, pi. It turns out that this matrix is closely related to the P by K topic matrix. Okay, so I will multiply this pi by 2 diagonal matrices. And these 2 diagonal matrices appeared in my pre-SVD and post-SVD normalization. I just now revert these normalizations. So I first revert the post-SVD normalization, and then I revert the pre-SVD normalization. Okay, then I will get a new matrix. It turns out that each column of this new matrix will be exactly proportional to one topic vector in the noiseless case. And the topic vectors are self-normalized, so therefore I can immediately get each AK. Okay, so this is the rationale. Then so part 2 of the algorithm. So the previous slide is for the noiseless case. Then in the real case, we have noise. So we want to see an exact simplex. So we need an algorithm to find the shape of the simplex from the noisy point cloud. It turns out that this vertex hunting is already actually a more than 30-year problem in the engineering literature, just for other purposes. So it's on low dimensional data. So we can find a lot of existing vertex hunting algorithms for that. Due to time constraint, I will point you to this recent paper for the survey of the vertex hunting algorithms. Okay, and then I solve this equation to get the barycentric coordinates for each point. Due to noise, some of the points will lie outside, a small fraction of the points will be outside the estimated simplex. Then the pi hat J star may have negative entries. Then I just truncate them and renormalize. Now I stack them together to get a pi hat. Then I reverse the post-SVD normalization and the pre-SVD normalization. I get this matrix A tilde. Then I normalize each column of A tilde to get my estimated topic vector. Okay. So I recall that in doing this, when we try to use PCA for topic model, we have 2 big challenges. But how did I resolve them in this algorithm? They were resolved using these 2 carefully designed normalizations. Okay, so we can view that the data matrix has a signal part and the noise part. The signal part is just the population or the frequency matrix. It admits a low rank structure under the topic model. Okay, so therefore, when I do pre-SVD normalization, I normalize the whole matrix D. Both the signal and the noise parts get normalized. So this can partially adjust the signal to noise ratio in SVD. Then after I get SVD, after I do SVD, I only keep those leading eigenvectors, singular vector, which are mainly driven by the signals. So the post-SVD is only on those signal parts. And the main purpose of the post-SVD is to produce this simplex structure. So without the post-SVD, we don't have any simplex. With SVD, post-SVD normalization, we get this simplex structure, and this simplex structure serves to connect the principal components with the target topic vectors. So this is how I resolved one challenge I posted before. The other challenge I posted before is that there is a severe heterogeneity in the data. Then both of my previous SVD and the post-SVD normalizations try to resolve this data heterogeneity. And I must consider their combined effects. So I have to design them carefully so that they coordinate with each other. And I cannot explain this in a few words. This is embedded in a lot of calculations in random matrix theory. Roughly speaking, if I choose the pre-SVD normalization, properly to cope with the post-SVD normalization, then I can show that even though the data has very severe heterogeneity, if you look at those embedded points, the noise level on those embedded points are roughly the same for all the words. Okay, and as a consequence of this, if we go through our analysis, then in the end, we can look at the estimation error allocated to each word. So if we look at the estimation error allocated to each word, and then you will find that it is proportional to the overall frequency of the words. And the higher frequency words basically receive more errors in this algorithm. Okay, and this has to be proportional to frequency, not a square root of frequency or frequency squared. Only if I get this proper allocation, I can get the theoretical optimality, as I will show you later. Okay. Okay, now how does this method work? So I want to show you the performance from both the real data analysis and the theoretical properties, and the simulation examples are in the paper. Okay, so this is a data set consisting of the Associated Press news in early 1990s. I pick k equals to 3. Then what I do is I just do SVD together with the pre-SVD and post-SVD normalizations, and that's it. Then I get a two-dimensional embedding for each word. Okay, so my theory tells me that I should see a triangle structure, and I indeed see a very nice triangle structure. What does it mean? It actually means that my theory fits this real data. So it means that the topic model is actually a very good fit to these real data sets. Then I can see the same result as I predicted in theory. Okay. And those words located on each vertex are the anchor words of each topic. But just reading these anchor words, we know that this topic represents finance, this topic represents crime, and this topic represents, this topic represents politics, this topic represents crime, and this topic represents finance. Okay. Then when I first presented the result, people asked me, it's not a triangle, you have a hole here, right? So first, based on our theory, we don't need to fill in the whole triangle. It's okay to have some parts empty. Okay? So then I started to dig into this empty area. What does it mean? It means no words in this area. If a word is exactly on this edge, that means this word is directly connected to these two topics, crime and finance, but has nothing to do with politics. It turns out that in 1990s, there indeed existed no such words. And my colleagues in the Harvard political science departments are very happy to see this because they think everything is about politics. And then we also look at the words on the other two edges. For words on these edges, they are related to this topic of politics and this topic of crime. And the closer to this vertex, the more related to crime. The closer to this vertex, the more related to politics. Similarly, these words are related to politics and finance. So these parts are more finance, and this direction are more politics. Okay, so using this real data example, we are pretty happy to see that it seems the model and the methods work very well. Okay. Then how about its theoretical performance? I'm going to show you the error rate. So I need some regularity conditions. The first is identifiability condition. Also in the second condition, I want to remind you that we have 3 dimensionality parameters. N is the total number of documents. Capital N is the document length. And P is the vocabulary size or dictionary size. Okay, so the requirement is that the N times capital N is much larger than P log N. And we will show that this cannot be relaxed from the lower bound result. Okay, then we notice that in practice, people always almost always do the pre-processing by removing those extremely low frequency words from the dictionary. Okay, so this requirement puts a mild condition on the lower frequency words. Okay, and we assume that they have been removed. Those really low frequency words have been removed in pre-processing. And then the last condition is a regularity condition, where the sigma W and sigma A can be viewed as the covariance matrices for W and A. Okay, and then we show that the rate for the error is in this form. Okay, so it's monotone increasing with the dictionary size and monotone decreasing with the number of documents and the document length. Okay, so in my first paper, I actually got this rate only in the case that the document length is larger than the dictionary size. I call it the long document case. Then for a very long time, I try to relax it because in practice, the average document length is usually very small. For example, for the text abstracts, paper abstracts, usually a couple hundreds of words. So just under the help of my very capable postdoc, Jiming Wang, we now push these results to the short document case. Now we just need the document length to be at the order of log n. Then for the whole range, no matter long document case or short document case, we get this clean result. Okay. Is this rate optimal? We have a matching lower bound, and we can show that this rate is already optimal up to a logarithmic factor. And using this lower bound, actually we prove this lower bound first. Then we actually can find that many of the existing algorithms are actually non-optimal. Okay, so among all the existing, only this paper can get the optimal rate in the long document case. They have no results for short documents. Additionally, their rate assumes no frequency heterogeneity, which is not realistic, but our rate actually holds under severe frequency heterogeneity. We don't have this additional factor here. Okay. So the main technique behind the proof is some very delicate entry-wise eigenvector analysis. So here I let Xi hat be the matrix of K left singular vectors. So if I put these K left singular vectors together, I compare it with the population counterpart. And then if we apply the standard, for example, sine theta theorem, we can look at the angle or the angle between these two linear spaces. Okay, so that corresponds to the Frobenius norm of this matrix subject to a K by K rotation. However, that Frobenius norm is actually about the aggregated error in all the P rows. But in order to get our optimal rate, we actually need to know the individual error on each individual row. And these errors are different for different rows. So basically, high frequency rows get higher errors, and it's proportional to square root of it. Okay. So it took us a lot of time to do this very delicate entry-wise eigenvector analysis. Only after we get this correct large deviation bound for individual rows, then we are able to get the final optimal rate. And we'll be able to show that the optimal rate is not affected by severe frequency heterogeneity. Okay, then so far I only talk about estimation of A. Remember, we have another matrix W containing the topic weights of all the documents. How about W? So in fact, for these kinds of problems, if you have two factor matrix, A and W, if you know one of them, the other will be very easy just by using the regression. So here we take the weighted least squares, and these weights are the same from the pre-SVD normalization. Again, it's just to adjust the effect of severe word frequency heterogeneity. And then we can show that we have the rate, and as long as the dictionary size is big O of n, it matches with the lower bound reported by other people. Okay, so if you don't have too many documents, so that n is small over p. Then in that case, we should estimate the W first. Here, the approach we take is we estimate A, get optimal rate, and then estimate W as a byproduct. So if this doesn't hold, then we should estimate W directly. Okay. So this finishes the estimation part. We now have a fast spectral algorithm for estimation, and its rate is optimal, it's computationally very efficient. Okay. Then I start to think about the conditions. So in this condition, in the regularity condition, we actually assume that we have strong enough signals. What if the signals are too weak? If the signals are too weak, the information theory tells us that we won't be able to estimate these parameters, but we may still do the global testing. So in this global testing, we just want to know if there exist multiple topics or if there is only one topic. If the whole corpus is just about one topic, then there is no need to run any topic modeling. So topic modeling makes sense only if there are indeed multiple topics. Okay, so this global testing problem is analogous to this global testing in many other high-dimensional problems. And in this paper, we found that, yeah, the signal strength required for global testing is indeed strictly lower than the signal strength required for estimation. Okay, so this is indeed it indeed requires weaker signals. Now I'm going to show you how I will do this global testing problem. And later in the real data analysis, I will show you that they can also be used for the in the real data. And due to the time constraint, I will keep this part really brief. Okay. So we propose the DELF statistic. So in this DELF, the idea is analogous to the chi-square statistic. If the null hypothesis is true, and then there is only one single topic, and this topic vector can be estimated from the average frequencies over all documents. And then the information for testing against the null comes from the deviation of xij from the ni times mu hat j. So this is very much like a chi-square test. But these data are not normal data. They are multinomial data. So we cannot do the standard chi-square. We need a careful debiasing procedure. Okay, so the bias comes from the non-zero mean of chi-square itself, and also from the plug-in effects where we don't see the true mu j, we plug in an estimated one. This can still be significant. So we need to carefully find a way to remove the bias. Okay. And then we also estimate the asymptotic variance of this DELF statistic. And then we can show that asymptotically, t divided by square root v converges to a standard normal. So therefore, we can easily control the type 1 error and compute the p-value without borrowing any like resampling or bootstrapping procedure. So this test is very convenient to use. Okay, and then this theorem combines several theorems from this paper. And this paper actually studies a more general setting than this particular setting. So I just adapted from the more general results. Okay, so we can show that first, we have this asymptotic null distribution. And this distribution is parameter free. Although our null is a highly conjugate null hypothesis, we actually still get this. That's because this with a proper pivotal statistic. Therefore, the level will be correct. Then how about the power? We show that if this goes to infinity, then this one goes to infinity so that we have asymptotically full power. And then a matching lower bound. If this goes to 0, then the two hypotheses are just indistinguishable. Okay. So this finishes the first part of the talk. And then I have two quick remarks, and I will apply all these techniques to the MetaStat data set I showed you at the very beginning. Okay, so I think the topic modeling is I feel it's a very nice area because the topic model can be extended to many different settings, and the Bayesian statistics already went very far. They extended the topic model to almost everywhere. But on the other hand, the computable methods and the statistical theory study are far behind. So this creates a lot of research opportunities here. Okay. The second remark I want to show you is that although I talk about a text analysis, it doesn't mean that it can only be applied to text data. So basically what we do in this topic model is that we have a factorization structure on some particular count matrix. And all these techniques can be extended to non-text data. For example, in genetics, we also have a lot of counts, allele counts. So it can also be modeled in this way. So I had one paper. Well, in this paper, we studied the traffic of New York City. It's also the count matrix, and we use basically very similar techniques as a topic model, and we get the topics, and each topic is interpreted as a particular traffic mode. Okay, so in the remaining time of the talk, I'm going to show you the application on the MetaStat dataset. Okay. So in our two papers, we actually did a lot of exploratory data analysis and just find some very interesting things. So here I showed the most prolific authors in this dataset based on different metrics. And the dataset is publicly available for downloading. And so if you are interested, you can study it by yourself. I introduced the two methods today. I spent most of the time talking about this topic score algorithm. So let's apply it to this data set. We did some pre-processing of removing extremely short documents and those stop words and extremely low frequency words. These are the dimensions and N and P in our we finally implemented. How to choose the number of topics is a question that deserves a separate discussion. For in this paper, we just choose K by combining different approaches, and we find K equals to 11 is a good choice. Then we apply topic score, we get A hat, matrix, the topic vectors. So for interpretability, we will do some normalization. So we normalize it in this way. So for each word J, we will normalize the corresponding row by the sum of that row. So this will adjust each word by the frequency. And then for each J, now after the frequencies are adjusted, we can see that which words are more likely to be the anchor words. If a word is an anchor word, then this vector has only one non-zero entry, that is 1. Okay. So therefore, we can, for each, if we fix a topic, then we can just arrange the words in the descending order of this A hat JK. So the more top-ranked words will be the anchor words for each topic. Now we can use these anchor words to give names to each topic. So these are the results. As I mentioned before, the signals in this data set is very strong. So just for any people with some expertise in our area, we can easily know which topics are. So here, so these top-ranked words, the estimated topics, and then these top-ranked words are outputted by the algorithm. And then the names for each topics are given by ourselves. For example, for this topic, if we look at these words, A optimum, D optimum, amber, non-regular design, we immediately know that it is experimental design. Okay. For some topics, maybe our name is not that appropriate. So you may come up with a better name. So for example, this regression topic actually combines the topics in like non-parametric regression, semi-parametric regression, and high dimensional regression. Okay. So this is the first part. We use a hat to answer the question, what are the main topics in statistics? And this is an objective answer, the objective data-driven answer. The next question, what are the trends and patterns in statistical research? We now use the W hat. Okay, so we get an 11-dimensional weight vector for each paper. And we now take the averages of these vectors in different ways. So one way is to take within the yearly average. And the other is to take the average for each author. Okay, let's look at the yearly average first. Here, for each year, we get an average weight vector that is in dimension 11. Okay, so for each year, we get 11 number here. And then when we plot, we actually fix each topic and then connect the points of different years. So this shows us the trend, the overall interests of our society on this particular topic in 1 year. Okay. Since these entries sum up to 1, so the average is 1/11. So the topics above this dashed line will be the relatively more popular topics, popular quotient. And then these are slightly less popular topics. Okay. And since these entries sum up to 1, if we have an increasing trend, it must be compensated by some decreasing trend of some other topics. Among these topics, we can see that 2 topics that receive a lot of increase in the past years is the bio and medical research and this machine learning topic. Okay, and the mathematical statistics and regression are the 2 topics that always have the highest weights, even now, but their weights are generally gradually decreasing. And how about the average over authors? So for each author, I can take the average of the WIs over the papers written by that author. And then for the representation purpose, I actually subtract from this 11-dimensional vector the overall average of all the papers. So therefore, the vector I plot here is a vector that the entries sum up to 0. If an author has a positive entry somewhere here, it shows that this author has a higher than average interest on this topic. For example, for Professor Carroll, we can see that he has higher than average interest in regression analysis. As I mentioned, this includes the non-parametric and semi-parametric regression research. And he also has higher than average interest in biostatistics and medical statistics. Some other example, like Professor James Berger is well known for his research in Bayesian statistics. So he has a very high bar here in Bayesian statistics. And Professor Fan, high bar in regression. Michael Jordan, very high bar in machine learning. Okay. There are some other authors whose research interests are more spread over different topics. For example, like David Donahoe, Peter Bickel, and Cunhui Zhang, and they are more like the theoretical statistics. They do the develop mathematical theory for all different kinds of topics. Okay. Then in my how many minutes? Okay, I will finish very soon. So and then also I introduced the global testing problem. Okay. Usually we think the global testing seems to be useless in real data because we rarely test this just one hypothesis for the whole data set. We almost always reject the null hypothesis that k is equals to 1. But the way we use global testing is to look at these smaller corpus. So we restrict only abstracts written by just one author. Now we say that within this smaller corpus, is there only one topic or multiple topics? Okay, so here n is usually small, but doesn't affect our asymptotic property, because our asymptotic property just assumes that the total number of words in all these abstracts go to infinity. This is usually satisfied. Okay, so I have no problem applying my test. Okay, then for each author, I apply the global testing technique I used. I get a p-value, and I get a z-statistics and a p-value. And these z-statistics can be used to measure the semantic diversity of an author. Then let's look at the results. As you can see, so here I plot the z-scores for different authors, and the x-axis is the log of their total number of papers in this data set. As you can see, it's true that usually those very productive authors also have very high diversity in their abstracts. Okay, so I have to say that the semantic diversity doesn't necessarily mean the research diversity, but I think it is indeed true that for these top-ranked authors, they do have a very diversified research interest, and they made significant contributions in many different areas. Okay, so I have some other results about the joint analysis of the citations and the text, and this will yield some journal ranking results and topic ranking results. Due to the time constraint, I will skip all of them, but point out you to this paper. So by the way, this topic ranking ranks bio and medical research in the bottom, which doesn't mean that this area is not good. We have a detailed explanation of why this is true. Okay, please see the paper. Okay, so for today, I introduced some techniques for these statistical techniques for text analysis. One point I try to make is that I think these statistical models are still very useful, even given the current trend of large language models. So we shouldn't abandon them. We should try to combine them with the LLM. And then I use topic modeling as an example, showed you some methods that are computationally fast and theoretically optimal. And then again, all of them are applied to MedStat, and the data set is available for everyone to use. And these are my co-authors. Thank you, everyone.
Oh, thank you for that very nice talk, Tracy.
Thank you.
Let's be mindful of Tracy and Ray's schedule here, but if anyone has any questions they would like to ask, then please go ahead and do so.
Thanks for the nice talk. And I have one question, very vague and just abstract question. And just like to make sure whether I understood correctly, the simplex geometry appears during the analysis comes from the fact that we have modeled the topic by the convex combination. Is it correct?
Yes, it partly comes from that.
So like it's just general question about topic analysis. I was always wondering, like, when modeling the topic, like it's possible to, like, instead of using the convex combination, we can have a square on the weight to make the structure as a sphere, which is usually used in quantum mechanics. And usually, like, spheres kind of gives you more kind of nice mathematical properties than simplexes. So I was wondering whether, like, people haven't tried those modeling, and would they make any differences? For example, like in analysis, just very vague question, I guess. Yeah, thank you.
Yeah, thanks for the. So you are suggesting that if we can relax the assumption that these weights are like non-zero and sum up to 1. So if we relax it, then this will no longer be the convex combination. Is that your question?
Oh, just basically like you can just translate, like it's equivalent to you can just plug in W square instead of W in that equation, which makes our entire like W space as a sphere instead of simplex.
Oh, I see. Yeah. So you may do that, but the topic model is very special because this omega I is a word frequency vector to put on this multinomial distribution. So we have the requirement that the entries have to omega I itself has to be a probability mass function. So this convex combination guarantees that you always get a probability mass function. So if we do other types of structures, it may not be guaranteed.
Thank you. Yeah.
Okay, thanks for the question.
Do we have any further questions? Okay, well, if there's no further questions, I'm sure you can write to Tracy and ask her if you think of something later, or if you're meeting with her, then
No problem. Yeah, I will be happy to discuss with everyone during the one-to-one meetings. And thank you everyone for attending this talk.
All right, yeah, thank you, Tracy.
Thank you.
All right.